anybody here tried Go? Is that pretty much everybody? Okay. So part of this talk is to try and sell you on why you should use Go, but this will probably be an easy sell. So before I begin, I want to ask everyone here 2 questions. The first question is, are computers getting faster? Who thinks that computers are getting faster? Show of hands. Computers are still getting faster. Interesting. I asked this question yesterday. All hands. Alright, so let's ask a different question. So, the people did raise their hand and say, how's that? Much better. Much better. So for the people who did put up there, yes. I'm just going to yell loudly. Is that okay? It's just actually so I can talk loudly. Is that okay?
Yes. It's not okay. You can't record your voice.
So the second question was, for the people who think computers are still getting faster, do we need to rewrite our programs to take advantage of this, or do we get it free? So we get free performance with faster computers. Okay. So to talk about that, to talk about writing high performance code, we need to talk about the hardware that's going to run our code. Something to note, we're all of us are software programmers in this room. And all of us have benefited from Moore's Law, the doubling of transistors every 18 months. In the last 50 years, we've experienced a 6-order of magnitude improvement in our tools. There is no other industry that has experienced that. Building, airlines, construction, telecommunications, maybe getting close, but software is has ridden this wave of ever improving tools for the whole of our lifetimes. But this is starting to change a little bit. This graph shows the number of transistors on a CPU, and it's still going up on a nice logarithmic graph, so that's still going up. But what's concerning here is processor speed has flatlined around, let's say, 10 years ago. And kind of more worrying is this graph here, which is the number of transistors, $1, 1 ruble, 1 euro, doesn't really matter, buys you. That's been increasing, so transistors are getting cheaper, except they stopped getting cheaper about 2010, and now they're getting more expensive. And this is because the process to shrink the transistors is costing Intel and AMD more and more and more. They have to invest billions of dollars every time they go from 20 nanometer to 14 nanometer to 10 nanometer. So what are all these transistors doing? Well, they're going towards adding more CPU cores. It's pretty straightforward. So CPUs stop getting faster, but they are getting wider now. And I doubt anyone in this room has a computer with them that has just one core. Like maybe this old iPhone, but everything else has more than one core. You can have pretty much as many as you want on the server. In fact, the number of cores you can have is determined mainly by heat. Sort of by price, but that's just because they're hard to manufacture. But mainly by heat. So why is heat a problem? Has anybody studied electrical engineering? Yep. Okay. So this is the simplest kind of logic gate here. It's just an inverter. And it's made in a technology called complementary metal oxide semiconductor, which it's called complementary because there are always a pair of transistors, one off, one on. They always switch roles. The key thing here is that because there's always one off and one on, the power dissipation is much lower. This is a group from integrated circuits in the 60s and 70s. The thing is that CMOS is the technology in every computer in this room. The television, the microphones, everything is the only technology that we have at this point. Now, when this inverter switches, it goes from high to low, and it goes from low to high. There's a brief transition where both of these transistors are conducting the on. One is moving from on to off, and the other is moving from off to on. There's a very brief period where technically they are both on. And because of that, there's a direct short. Power flows directly from the source to the drain, just like dropping a live wire over a train tracks. Now this short is very small, picoseconds, but when you consider that there are billions of transistors on a CPU, and this switching is happening billions of times a second, like that's billion gigahertz, all these little shorts add up, and that's just, it's like a bar radiator, it's just heat. So power consumption of the chip is directly related to the switching speed, how fast you want it to go. So there's this thermal headroom that we can't make CPUs go much faster because they just they can't take that heat. So what we know is that making the transistors smaller isn't really aimed at performance. It's kind of a side effect of what making the transistors smaller is aimed at is reducing the power consumption. And it's not so much about, low power, save the environment, save, recycle. It's literally making sure that the CPUs don't burn up. Try this one. And so, over the last decade, especially on the server, this is why we add more cores, because it's no longer possible to just make a single CPU faster. And so because of that, to take advantage of these extra cores, we need software to support that. Should I speak slower? Or is it okay? Okay, good. So, meanwhile, on the memory side of things, the memory attached to a server has increased geometrically. When I was growing up, my computer in the 80s had kilobytes of RAM. Thank you. When I was writing my essays in high school, I had, I think, 1.8 megabytes of RAM that I wrote all my essays in. Nowadays, servers have tens, hundreds of gigabytes of RAM. If you're working in the cloud space, you probably have upwards of a terabyte. So it's not a problem to have as much memory as you want. But the problem is that even while CPU speeds have taken off like this, memory speeds are lagging behind. So you can have a lot of memory, but the larger the memory is, the more chance that it's going to take a long time to access it. And this means computers and us computer programmers rely heavily on the cache. Like, we need caching to hide the memory latencies. And there's a problem here because the CPU cache has always got to be very small because it's fundamentally limited by the speed of light. If it was really big, it would take longer to access. So this is a picture, I think, of the last generation Xeon. And I think on the spec sheet, it says it has 12 megabytes of cache. But it doesn't really. It has 256 and 256 and 256, just all kind of spread across the CPU. So they're actually a bunch of little caches connected together by these links. So to bring this back to programming and to Go, why am I talking about hardware at a software conference? 10 years ago, maybe, if you were writing in Perl or Python, those great languages of that era, maybe some Ruby, there was a strong argument to be made that it's not worth investing engineering time in optimizing the code, because when you go to buy the server next year, the same money that you paid this year will basically buy you twice the performance. And this was definitely true in the 90s, like in this great heyday of CPU speed increases. But this isn't really true today anymore. If there are any C++ programmers in the room, you probably know Herb Sutter. He's the chair of the C++ committee. And he wrote in 2005 an article called "The Free Lunch is Over." And in his article, Sutter discussed all the things that I just went through, that you can no longer rely on fast hardware to fix slow programs. A decade later, I don't think there's any doubt that Sutter was wrong. He was absolutely right. Clock speeds are going backwards, caches are too small, and if you're hoping for that simple world of a single-threaded CPU, so you don't have to think about data races and concurrency and deadlocks, unfortunately that world is behind us now. So it's time for software to do its part. It's time for software to step up and come to the party. Rick Hudson, who's one of the architects of the garbage collector in Go, talked about this at GopherCon in 2015. He said, it's time for programming languages that work with the limitation of today's hardware, not ignore it. And he called this a virtuous cycle. If we write programming languages that work well with the hardware, then the manufacturers will be encouraged to build hardware that works well with our programming languages. And so, some of the things that I think a modern programming language needs to work on modern hardware, and this, I don't think this applies just to Go, I think this is general advice, is that they should be compiled, not interpreted. And there's nothing wrong with interpreted languages, but the interpreters themselves are operate very badly with the CPUs. They operate badly with branch prediction. They have poor code locality. A lot of things which means that they just can't be made to run as fast as native code. Permit efficient code to be written. This is fairly straightforward. Your language should let you talk about bytes and addresses and words of memory and machine-sized things, rather than Python or Node, which talks about just this kind of idealized number, which has no dimension. That's convenient, but it comes with overhead. It lets programmers talk about memory efficiently, and this, I think, is one of the most important things. We saw on the slide the difference between CPU speed and memory speed. So if your language forces you to use a lot of pointers, then your CPU will be slowed down doing cache misses, following pointers all around this gigantic address space. And fundamentally can scale to multiple cores, has some notion of concurrency built into it. And so the good news is, for everyone in this room, that the language I'm talking about is Go. Probably you've already sold yourself on this. Now, when I talk to people about Go, and perhaps when you talk to other people about Go, these are some of the things that are usually said about it. You know, the static binary, the powerful concurrency features, and the efficient compiled code. And I'm really going to focus mainly on these last two in the rest of this presentation. So I want to go back to the Go's concurrency story and talk a little bit about how we arrived at the idea of Goroutines. In the beginning, mainframe computers like this did one thing at a time. If you were a programmer, you submitted your program,
and an operator would load it, and you would have the entire machine to yourself till it ran or till it crashed or whatever. And then you got the result back, someone would print it out, and they would give it back to you. And these machines for the time were relatively powerful, but the latency of writing and debugging a program was terrible. It was measured in days. Like if you didn't have high priority, then you may not be able to run your program more than once a week. And if you were trying to do a tiny little change, you had to wait a week to see the results of that. Now, in the 1960s, computers had become a little bit cheaper, relatively, and so they could be afforded not by single institutions, but departments and individuals. And so this led to the notion of a small group wanting to share a computer, and so we have the rise of time sharing and more interactive forms of computing. Now, by the 70s, this idea of multiprocessing, having multiple processes, running multiple processes on the single machine was well established, especially for writing network servers. Telnet, FTP, login, send mail, all treated a connection to a server as a single process. This is the original web server this is the original machine that Tim Berners-Lee wrote the web browser and ran the first web server on. And it followed this model. When you would make an incoming connection, the server would fork a whole process, talk to you, and that process would send the result back and then clean itself up. And this is the kind of heart of time sharing. This creating the illusion of doing more than one thing by rapidly switching the CPU between tasks that it has to do. We call this context switching. This is an image I took from Wikipedia that shows all the registers that you can address as a programmer on Intel. And this represents about 4 kilobytes of data. From all the MMX registers to the extended AX, EX, DX, all the segment registers, the control registers. This is all information that, as a programmer, the compiler will expect to be able to write into. And so, when you do a context switch, the operating system has to save the entire state, every single one of these registers, because it has no knowledge of where you're using them or not. So it can't take a risk that you've stored some useful information in here and not record it. So a context switch is basically recording all the information in the CPU registers, storing that somewhere else, then getting the information for another process, writing it back into the registers, and then going on with that process. So this takes a fair amount of time, relatively speaking. The other major cost of doing a context switch is each process has a different view of memory. It has its own memory mapped into the address space. And so when you switch processes, you need to switch those mappings as well. And this is an expensive operation because it uses a very limited cache called the transaction look-aside buffer. And then lastly, there's just the overhead of the scheduling algorithm. When it decides another process has to run, choosing which one, prioritizing them, that kind of thing. Now, most of these costs are fixed by the hardware. Every time Intel adds a new register, that's just more data to save. And because of this, rapid context switching, like having too many active processes, are some of the things that grind servers to a halt. They spend all of their time doing the context switching and not enough time doing actual real work. So this led to the development of ideas like threads. And threads are similar to processes in that you save and restore the CPU state, but threads share memory. And this also enabled the ability to do more than one thing at a time. If you have multiple CPUs on the server, they can be multiple threads executing within the same process. But as I said, they still incur a lot of the costs of the overhead of context switching. So in Go, Goroutines take this idea a step further. Goroutines are cooperatively scheduled inside the process. We don't, for each Goroutine is not mapped onto an operating system thread. And the switch between Goroutines, when it decides to give up its time for another, happens at points like this. When you send and receive on a channel, if that send or receive would block. The go statement, which is the way that you start a new Goroutine from another. Doing an actual syscall, like talking to the network, talking to the disk, or after being stopped by garbage collection. And the takeaway from these is that all of these points happen when your program can't make forward progress. It's not having its time stolen. It basically got to a point where it needed import or needed to communicate with another Goroutine. So it's no big deal to give up its time for another Goroutine. Goroutines are multiplexed onto operating system threads. There is no one-to-one mapping between a Goroutine and a thread. What generally happens is you have if you have 4 cores, you have 4 threads, and they just work through servicing all the Goroutines in a program. This makes Goroutines very cheap. It makes them cheap to switch between because this happens inside the Go program. There's no need to coordinate with the operating system. And it means that Go programs can be written to just assume that you can have tens of thousands, hundreds of thousands. The scheduler scales, it's assumed at least 1 million Goroutines in a busy program. So they are much cheaper to create and use than threads. Now, another part I want to talk about of how Go does this is stack management. This is a stylized diagram of the process address space, like memory runs from the bottom of memory to the top. I would have put it from top to bottom, but it doesn't fit on the slide like that. And so normally, when you load a program, it goes somewhere near the bottom of memory. And then you have the heap of the program and the stack. And as the program runs and you allocate more data on the heap, this is going to grow upwards. And the stack, if you're recursing into functions, is going to grow downwards. And so if these 2 arrows would ever meet, this could be catastrophic. Your stack could overwrite some data on your heap, or the other way around. So to prevent against this, most operating systems create this thing they call a guard page, which is an area of unaddressable memory, so that if either of these arrows touch the page, the program will crash, rather than continuing with slightly corrupted data. Now, when we're talking about a multi-threaded program, this gets a little more complicated. We still have the heap and a stack and a guard page, but because we're going to run multiple threads, you can see that they start to compete for the heap's address space. And the other thing is that because we have to place these guard pages at known points, we have to decide up front how much stack we want to give each thread. It's a static allocation for the lifetime of the program. And so this is really a choice. Too little, and you recurse a little bit and hit the guard page and your program crashes. Too much, and you just consume huge amounts of address space, and it limits the number of threads you can use. Okay, yep. So we've seen how Go runtime schedules a large number of Goroutines onto a number of threads. But what about the stack requirements? How do we deal with that? So we do things a little bit differently than the static allocation. we have each Goroutine gets a small stack. It's about 2 kilobytes, and that's just taken from the heap. And every time a function runs, we check to say, just before we actually do the body of the function, we check to say, are we beyond this limit? So when H runs, it's above that limit, and we can't run it. And that check then fails. We trap into the runtime, which allocates a larger stack area. We copy all the contents of the old stack frame, and we free the old one. So by having this cheap check at the start of every function, we have the ability to grow the stack as we need. And now H can run. Okay, and the last bit I want to talk about is the integration of network polling and the Go runtime. I don't know if anybody's read this page. This was called the C10K problem, and it came out in 2002, so the numbers are a little bit dated, but it was really a question of how can we, with the operating systems and the hardware of the day, write a server that can support 10,000 connections. As people worked on this problem, 2 strategies emerged. Threads, so a thread per connection, or an event loop. Now, almost all operating systems support this nature of handling many network connections efficiently. You give your connections to KQ or ePOL, and then you just sit and wait for notifications. This is at the heart of an event loop. Are there any node programmers in the room? One? What about Twisted Python? Any Python? Yep. So what are the things you like about that model? Well, you get high scalability, it's efficient. But the downside is that, at least in my opinion, you have to adopt this quite convoluted callback style. Like with Twisted, you have callbacks and errorbacks, and Python, it's promises and functions past to futures. So what I think is that Go actually provides programmers the best of both worlds, because we manage the event loop under the hood, but you still get to write straightforward imperative programs. So how this works under the hood is that we have one Goroutine which is running ePOL and communicating back to other Goroutines when their connections are ready. Now, the naive way of doing this would be to use a channel to kind of communicate some message between the Goroutine wanting to read from the network and the one that's waiting for that signal. And this is how it worked for some time. But the problem with that is latency. This channel send and receive, even though it's to do with network traffic, is treated the same as any other channel send and receive. So to do that, to improve this, the scheduler and the Go scheduler and the runtime poller are aware of each other. And so when a packet comes in on the network, we know which Goroutine was waiting for that information, and rather than use a general channel send mechanism, we actually just wake that Goroutine straight up. We put it straight back onto the run queue straight away. This is a screenshot from the execution tracer, which I'll be talking about in this room at the same time tomorrow. But what I want to kind of highlight is here is there is a line saying some network activity, and you can see there's a direct link to starting that Goroutine straight away. And the effect of this is that by reducing the latency between the transfer signal being the signal the data is ready and the Goroutine being ready to consume that data, is that we keep buffers drained so they don't fill up and reduce TCP windows, and we just reduce the latency between I/O operations. And so, to summarize, Goroutines give you this powerful abstraction effectively for free. They free you from worrying about event loops and thread pools. The stack of a Goroutine is as big as it needs to be. And you don't need to be concerned about pre-allocation or running out of memory. And this is what enables us to have tens, hundreds of thousands of Goroutines in any program without really any resource limitations. And the network polar lets Go programmers avoid this callback style of programming, but you're still able to leverage the efficiencies of epoll and KQ, the efficiencies of the event loop. And finally, the runtime, just make sure that there are just enough threads to service all the Goroutines that need to run, and keep your cores active without the need to have a thread for every single Goroutine. So this reduces context switching costs, this reduces just general thrashing. And fundamentally, and the reason why I wanted to come and explain this to you today is that from my point of view, all of these features are transparent to you as Go programmers. You just write normal Go code, and all of these, the runtime works to make your programs fast under the hood. You don't have to think about these things. There's obviously more to go that I haven't talked about. Super fast compilation, I'm very proud of our compile speeds. I wish they were even faster, but it's something that helps us bridge the gap between languages that have a REPL, like Python or Ruby, where telling people you have to compile your code before you can run it is a foreign step. By keeping the compilation speeds low, the compilation speeds high, it helps bridge that gap. The excellent tooling, built-in build, test, code formatting, vet and lint. The documentation comes directly out of the source code using a simple convention. So if you used a PyDoc, it's like that. Built-in race detector written by Dmitry Vyakov of Moscow. Excellent cross-platform support. Cross-compilation for people, almost everyone develops on their Mac, but they run their code on Linux. And the cross-compilation support in Go is second to none. It literally takes no more steps to build your program to run on Linux as it does to run on a Mac. So, if you'd like to know more, and I think I'm probably preaching to the converted here, I think everyone at least is interested in Go, there's the tour.golang.org. It's an interactive online tutorial. Go join a meetup. Go join the Novosibirsk meetup here. And if you want to watch more Go talks and more presentations, Damian Griesky maintains goforvids.appspot.com, which is an index of all the recorded videos on YouTube and things like that from other Go presentations. So with that, thank you very much for your time.
Thank you, David. Any questions?
You want to yell it out and I'll repeat it?
So, I'll give you this one for answering.
Yep.
So, is it working? Yeah.
Hi, Dave. Thank you for the speech. Very interesting. I have two questions. First of all, do you use any IDE for Go?
So the question is, it still doesn't work. The question is, do I use an IDE? I personally don't, but I know that there are many people that do. My reasons for that are not very well founded. They're mainly in my experience for most of my career I've been an SRE or an operator, and so I'm used to interacting with servers over the terminal. So I'm much more comfortable with command line tools like Vim or Emacs if that's your thing. I do know that JetBrains are out there, the makers of Gogland, and you should go and talk to them if you're interested in a Go IDE. There's also VS Code, which seems to be very popular as well.
Second question, there is a myth, Go programmers don't like debugging. It is true?
So the question is, there is a myth that Go programmers don't like debugging. Go's GDB support has historically been quite ordinary, like quite not very good. There are 2 people at Google tasked with improving the dwarf support. So Go will look better in GDB. And there's also Delve, the debugger. And I know that Delve also works well with Gogland as well. So personally, I don't use debuggers, and this could be because they've never worked very well. Like this could be a kind of a symptom. But one thing that when Rob Pike was asked about this question, he said that debuggers don't make any sense in concurrent programs. They make a lot of sense when you have one thread of execution in a program, but when you're debugging a multi-threaded programming with many Goroutines, there's this ambiguity between, should I stop all the Goroutines? Every time I press S to step a single instruction, should all the Goroutines step an instruction? So there are probably some questions about what does debugging mean in a multi-threaded program, but I do understand that coming from other programming languages like the interactive debugger with Java, like I used to use Eclipse, it was fabulous. I understand that it is a fair question to say what is the debugging story on Go, and my answer to that is Delve is probably the best solution at the moment.
Okay. More questions?
Just yell it out, or
Yeah. Was earlier.
he was first.
Thank you for your talk. And my question is, so after using Go even in some production projects, not for long, like for half a year, I still don't feel like that after coming from C and from Java, I don't feel like I understand how to properly write this code. So for Java, I know how to do that. For C, I know, but for Go, no. And so, what resources would you recommend for this? Thank you.
Why have the microphone? Is it specifically about? Is it how to write Go code in general, or something specific like how to do network programming, or web programming, or concurrency? So there are a wide range of web programming with Go style books. I have not read a lot of them. It's not really my area. Okay. Okay. Yeah, I think what I would. Oh, I don't have the internet. The best book that I know about Go, like the best general purpose book that I would recommend to everybody, is the book by Brian Kernighan and Alan Donovan, GOPL. It's called gopl.io. That's the URL, and I think that gives a really good background of not just Go the language, but the important parts of the standard library, including network programming. We should talk. We'll talk later. We'll talk. Yep.
Hello, thank you Dave for your speech. I want to know some bloody internals about the Goroutine stack. Does it share it between several Goroutines, or each Goroutine have its own stack?
Each Goroutine has its own stack, and they all are allocated on the heap, just like other objects. So, yep. Do you want to leave it with him? I'll just shout.
Well, if you insist. Then, if I understood correctly, the mechanic behind the stack is just like a dynamic container. So when we hit the limit, we just make it bigger, allocate more space, and copy the internals. Well, this doesn't sound like a very fast thing to do. And following questions to this: can we control it? Can we resize for some Goroutines? Plan more of space in advance?
So there are two parts to this question. The first one is the actual growth, which is by copying. I won't show the slide. One thing that Intel processors are really good at is copying memory. Like you set them up to copy 2 kilobytes from here to here. They are really good at that. So in terms of the growing by copying, I can't think of a report that's ever been a problem. Because don't forget, it doubles geometrically. So 2K, 4K, 8K, 16K, 128K. Like that's only 5. You only need to hit that limit 5 times, and you've increased your heap by five times. So it generally doesn't tend to be a problem. The second part of your question is how can we control, I guess, the initial size and the limit. That is an open question. So for example, we picked the value of 2 kilobytes. More or less arbitrary. It has gone between 1 and 4 kilobytes, and so we picked that one. For some programs, you want more. Like if you're writing a parser which is recursive, you're going to need to have a bigger stack. And for others, you may need a Goroutine which is literally just joining 2 channels together. So it's never going to make another function call. So 2 kilobytes might actually be too much. And there are 2 efforts underway that I know. One is to either have a kind of runtime call. So at the start of your Goroutine, it's like, please grow the stack. The other one is to use escape analysis, where we can kind of infer. It looks like during compilation, the pattern of this code is going to recurse. So we should start it with a bigger stack. So one is kind of deliberate, like you have to call a function. The other is maybe using some heuristics during compilation. Both of those are still work underway, and yeah.
Well, I have C++ background, and we don't really like copying much. That's why I asked this question. One more thing about Goroutine switching. You mentioned first that with threads, with context switching, we have planning overhead. And then you said that Goroutine switch at this point, this point, this point, this point. As far as I remember, these points are used very intensively in threads planning too. And second question with this, can you explain please what does it mean that Goroutine switch in the user space and how it affects context switching?
Okay. I'll answer the second part first. Where user space is what we call the program, and kernel space is you have to take a syscall to talk to the kernel. So there have been a bunch of studies. If you come find me later, I'll show you the paper that look at just the overhead on terms of cache impact of just doing a syscall, not the actual work it does, just the movement from the user process space to the kernel, like doing a switch and back again. So the general belief is that doing these operations without talking to the operating system is cheaper. So, and the first part of your question was around at which points do Goroutines?
No, not about which points, but when we talk about threads,
Yes.
Planning and around this point is over. But how Goroutines using the same points doing it more effectively?
Okay, let me go back to the. So these operations can either have a fast path or a slow path. If you're communicating between 2 Goroutines on a channel, if that's buffered and there's space in the buffer, then the send effectively happens straight away, and the receiver will come and get it out of the buffer later. if the channel is unbuffered or if the channel is full, then you can't put your item into the buffer until someone has already taken one out, created space for you. So effectively at this point, your thread of execution cannot make progress. You're blocked. So at that point where you're blocked, instead of spinning and waiting, the actual inside the channel send function, it goes to the scheduler and says, give my time up to somebody else. I cannot make any more progress at the moment. Give my time up to somebody else.
Doing the same job. When thread block, Cisco or memory query, well, it's just make context switching. How Go makes it more effective. The same idea basically.
Okay, so I want to compare Goroutine switching between it to thread switching between it. Threads switch between you switch between threads usually via a timer. So the operating system says you have such amount of time depending on your priority, and at the end of that a timer fires, the operating system records your context and gives the CPU to a different thread. That's on the thread side. In the Goroutine world, a thread is assigned to run a group of Goroutines, like a run queue of Goroutines. And so every time it goes back, the runtime calls back to the scheduler, it just takes the next one off the stack and runs that on the same thread. So generally you have as many threads as you have cores rather than as many threads as you have Goroutines. And this switching between Goroutines happens entirely inside the program without having to talk to the operating system. We can talk afterwards and I'll show you a diagram of how that works.
So the main problem that this stability is found out earlier in user space.
Yes, it's handled inside the program, not by the operating system. Yep, one more question.
1 minute.
Okay.
One short question, okay? Okay.
So thanks for your speech. I'm a novice in Go world, and I heard many times that Go is suitable for small microservices or some CLI utilities and so on. But what if I want to build a big application? Should I use or choose Go? And at other side, if I want to choose Go, should I use microservices or build a monolith?
So, yeah. So the question is Go suitable for large applications? Absolutely yes. This is one of the design points about the language. It was designed for big programming teams at Google, like tens, hundreds of programmers, tens, hundreds of millions of lines of code. You can absolutely use that for. Microservices seem to be very popular in Go because of the deployment story. Like, it's very easy to deploy them, so that goes well. But microservices are fundamentally a choice by the development team of how to carve up your organization. Like, rather than one contribute to a monolith, you have 5 teams working independently. Go can be used for either of them. Okay. Thank you.